Yeah, let me first of all thank Nemani for arranging this talk for me. Let me start with the abstract. Before that, I want to say something. I hope the high energy physicists here will bear with me, because what I am going to talk about will be too elementary for them. So any high energy physics experts can doze off. But please wake up when I come to my punchline. Okay. Next. So this abstract you might have read, but anyway, let me go through it. 100 years of fundamental physics have culminated in a theory called the Standard Model of High Energy Physics. This theory is now known to be the basis of almost all of known physics except gravity. I would like to stress this sentence, because what I am going to talk about, what is called Standard Model of High Energy Physics, is the basis of almost all of known physics except gravity. It is not just some obscure corner of physics. Anybody who has anything to do with physics, in my opinion, should know Standard Model up to a certain level at least. That is the first message which I wanted to leave here. Although the discovery of the Higgs boson 2 years ago in 2012 has established this theory, gravitational force has been left out. The energy scale of quantum gravity, known as the Planck scale, is 16 orders of magnitude higher than the presently accessible TeV energies. TeV means 10 power 12. 10 power 12 electron volt, and you need 16 orders of magnitude more in order to incorporate quantum gravity into physics. This is a crisis in fundamental physics that can be met only by the discovery of new principles of acceleration. So that will be the theme of this talk. So 100 years of fundamental physics. The earlier part of the 20th century was marked by two revolutions that rocked the foundations of physics. One, quantum mechanics; two, relativity. Everybody knows about it. Everybody in this audience will know about it. Quantum mechanics became the basis for understanding the atoms, and then coupled with special relativity, quantum mechanics provided the framework for understanding the atomic nucleus and what lies inside. So again, I am repeating. At the beginning of the 20th century, the quest or the search for the understanding of the atom topped the agenda of fundamental physics. This quest successively led to the unraveling of the nucleus, the atomic nucleus, and then to the constituent of the nucleus, namely the nucleon, proton or neutron. Now we know that the nucleon itself is made of 3 quarks. This is the level to which we have descended at the end of the 20th century. The depth or the distance scale probed thus far is 10 power minus 17 centimeters. That is the most important number which I would like people to take home. We know fundamental physics now down to the distance scale of this 10 power minus 17 centimeters. So this inward bound journey I have captured here in this rectangle. 100 years ago, more than 100 years ago, we started with atoms of dimension 10 power minus 8 centimeters. We went through nuclei and nucleons of dimension 10 power minus 12 centimeter and 10 power minus 13 centimeters. We have reached down to the level of quarks. The quarks, which are the constituents of the nucleons, as well as the electrons going around the nuclei to form the atoms. Both quarks and the electrons are now known to be point particles down to this distance scale, the same distance scale. What lies inside the quarks or electrons, we do not know, so I put a question mark. But the world's most powerful telescope, namely the Large Hadron Collider, which will soon begin to operate again, might discover something new that may come in newspapers in the next years, but that is for the future. So we are not going to talk about that. This inward bound path of discovery, unraveling the mysteries of matter and the forces holding it together at deeper and ever deeper levels, has culminated at the end of the 20th century in the theory of fundamental forces based on non-abelian gauge fields. So I will try to explain that, that phrase, non-abelian gauge fields. For this theory, we have given a rather prosaic name, Standard Model of High Energy Physics. I wish somebody gives a more poetic or romantic name, but anyway, for the present we call it the Standard Model of High Energy Physics. In this theory, the strong forces operating within the nuclei There are seats here, I don't know why you are standing there. You like to stand? In this theory, the strong forces operating within the nuclei and within the nucleons, as well as the weak forces that were revealed through the discovery of radioactivity by Becquerel 100 years ago, more than 100 years ago, are understood to be generalizations of the electrodynamics of Faraday and Maxwell. That should be good news for everybody who is outside high energy physics, because that the electrodynamics of Faraday and Maxwell is bread and butter stuff for everybody, every physicist. So what we are talking about is only a generalization of that. So that is the main message here. These electrodynamics, the basic electrodynamic equations which go under the name of Maxwell's equations, were written down by Maxwell around 1875, maybe a little earlier. The 20th century owes a lot to the Faraday-Maxwell electrodynamics. For the applications of electrodynamic technology become a part of modern life. We cannot just imagine anything in modern life without that. Now this dynamics of strong and weak forces, which I call the standard model of energy physics, I said it's a generalization of electrodynamics, and that generalization got worked out by the year 1975. So that is almost exactly 100 years later. So the moral is obvious. Equally profound applications, as the applications which we are enjoying now, will follow once the technologies of strong and weak forces are mastered. But that is for the future. What we are doing is studying the physics of the strong and weak forces with electrodynamics. We are barely scratching the surface. It is like, when electricity and magnetism study started, people were rubbing a glass rod against silk and things like that. That is what we are doing. So much more has to be done before it can be incorporated and assimilated, and then the technologies will follow whether we like it or not. I myself don't like it, but anyway, I cannot prevent it. Technologies will come. whether we like it or not, somebody will do it. Next. So the four fundamental forces of nature which govern the universe are given here. Almost everybody would have seen it in some form or other. The strongest force known to us is what is called the strong force. That is the force which binds the quarks together to form the nucleon, namely proton and neutron. And then it is the same force, a part of it, a residual strong force, which binds the protons and neutrons to form the nuclei. And it's the strength is measured by a strength parameter, which is of order of magnitude of unity. This is the strongest force known to us. However, it is felt only if you can probe down to the level of 10 power minus 13 centimeter. So that is the range. Next comes electromagnetism, which binds, once you have the nucleus bound by the strong interaction, electromagnetism binds the outer electrons to the nuclei to form the atoms, and then binds the atoms together to form the molecules, and then the molecules together to form all forms of matter which we know, solids, liquids, and so on. It is measured by a force parameter, which is the famous number 1 over 137, although it is not an exact number, it is actually many decimals, it is known, the fine structure constant, 2 orders of magnitude lower than this. So all the macroscopic phenomena, everything which we study in physics, please come and sit down here, there are seats here. Surface tension, viscosity, or elasticity, anything which we study in physics is a consequence of electromagnetism only. It is a manifestation of electromagnetism only. So that is the importance of electromagnetic force. And its range is infinite. It doesn't really get cut off exponentially as the strong interaction is. It exists even at infinity. The Coulomb force, although it dies down as 1 over r squared, the potential dies down as 1 over r, it in principle exists infinite, even at infinite distances. So its range is infinite. Next comes the weak force, which is a disruptive force, which is responsible for the decays of many of the heavy nuclei. That is how it was first discovered, in the form of beta radioactivity of nuclei. And it is a weak force which is responsible for the decays of most of the particles which we will be talking about. Weak interaction has another important role to play in the universe. It is the weak interaction which is responsible for the thermonuclear fusion reactions which keep the sun going, giving us heat and light, and without that there is no life. So for life, weak interaction is absolutely essential. And it is measured by a coupling strength which has a dimension of inverse of mass squared in these funny units which I am using, and if we use the proton mass squared in the denominator, its strength is 10 power minus 5. That is why it is called the weak force, weak interaction. And weak interaction also is limited in range. Its range is even smaller than this. It is given here as less than 10 power minus 14 centimeter, but the precise range is now known. That is a consequence of the standard model story, which I will mention later. I hope I don't forget that. Finally comes the gravitational force, which is the most important force. Because through gravity, which we are all stuck to the earth, otherwise we will all be flying in space. And it is gravity which binds the earth and planets to the sun, binds the stars to form galaxies, and binds the galaxies to form galactic cluster, and so on. So for the universe at large, it is gravity which wins over every other force. This is the most important dominant force. However, its strength is even smaller than this weak force. Its strength is measured by the famous Newton's constant of gravitation, which measured again in similar units using MP, the mass of the proton, in the denominator, proton mass squared. It's 10 power minus 40. Even 35 orders of magnitude weaker than the weak force. So why does it dominate? I'm sure all of you know. This is also, of course, long range like electromagnetism, but it is 38 orders of magnitude weaker than the electromagnetism, but still for the universe that dominates, because electromagnetism comes in both varieties, both repulsion and attraction. It can be completely nullified by choosing the charge, both the positive and negative charge equal. There is no such thing for gravity. More mass, it goes on adding only. There's always attraction only. That is why this number, this small number, gets compensated by huge masses in the universe. All of that everybody knows. Okay, this is the classification which is given even in the school textbooks. I think +2, the old NCERT books had this already. But this classification now should be regarded as wrong, because now we know that both electromagnetism and weak are not independent forces. They are two facets of one force called the electro-weak force. Electromagnetism and weak are two facets of one force called electro-weak force. That is one of the main components of the standard model, which we are going to talk about. And the nature of this electro-weak force and strong force are now so similar to electromagnetism. That's why I said that it's only a generalization of electromagnetism. That there is a strong temptation to unify these electroweak also along with strong. That has been called grand unification. That theoretical step has been taken some time long ago. Many theorists, even here, many all over the world, are studying that. But that is at the moment only a theoretical step, because there is no clear experimental evidence in favor of it. We do not know. It may be true, it may be proved in distant future. So for the present, if you run a timeline here, we are somewhere here. So electroweak unification has occurred in the standard model, but grand unification is for the future. Of course, the grandest of all unifications will be to unify gravity also, the fourth force also. That's what I call total unification. That was the dream of Einstein, but gravity has not been incorporated into the quantum mechanical framework. These three forces are incorporated into the quantum mechanical framework, and that is the standard model about which I am going to talk about. That has not occurred for gravity. So that is the second part of my talk. So once that occurs, all this may be true. So that is also for the future only. Okay, now since I said that everything is a generalization of electrodynamics, it's better to start with electrodynamics. For this audience, perhaps I should not spend too much time over this, but these are the basic laws of electrodynamics. The electric field vector E and the magnetic field vector B, how they are related to given charge density distribution and current density distribution is given here. So the space-time behavior, the space-time dance of electric and magnetic fields all over space is given by these famous equations of Maxwell's equations, 4 partial differential equations. Maxwell wrote them down basing himself based on the earlier experimental results of many experimenters. I mentioned 3 of them: Oersted, Ampere and Faraday. There were still many more. Chiefly Faraday one should mention because of his important contribution in experimental research, which gave rise to the whole phenomena, whole theory of electromagnetism. In fact, Faraday had a profound understanding of the electromagnetic field already, even before Maxwell came. In fact, Einstein somewhere says that the most important fundamental conceptual advance is the introduction of the concept of field existing everywhere. See, Newton only talked about matter, particles, which he could see, anybody could see. But Faraday imagined something which we don't see and which dominates. We know, I mean, there are fields, electromagnetic fields dancing about everywhere here. Your cell phone you operate and then you are able to hear. So that was Faraday's important contribution. In fact, Maxwell in his book says that all he did was to put Faraday's concept of electromagnetic field into mathematical form. That's what Maxwell says. He was being a little bit too modest because, as all of you know, he had to introduce this important displacement current term into the fourth Maxwell's equations. Otherwise, the equations were inconsistent with charge conservation. But anyway, once Maxwell wrote down this complete and consistent system of equations, the Maxwell's equations, important consequences followed. Maxwell himself showed that electromagnetic disturbances follow existence of them, or the electromagnetic waves. The existence of electromagnetic waves he proved from these equations, and not only that, he could calculate the speed of those electromagnetic waves, and when he calculated it, it came out to be 3 into 10 power 10 centimeter per second. And by that time, the speed of light had been measured to be exactly that number. So Maxwell jumped to the conclusion that light is nothing but an electromagnetic wave. This was an important discovery because until then nobody knew what light was. People knew that it was a wave. The diffraction and the interference experiments of Huygens, Fresnel and Young had shown that it was a wave, but what wave it was only Maxwell who solved it. And then Hertz experimentally established the existence of Maxwell's electromagnetic waves, and then Marconi, Jagadish Chandra Bose showed ways of how to generate and detect them, and that led to all the applications which all of us know. Now this system of equations, excuse me, I'll take some water, feel my throat gets dry. This system of equations, Maxwell's equations, have stood the test of time now for more than 150 years. Even the two revolutions which I mentioned at the beginning of the talk, which shook the foundations of physics, namely relativity and quantum mechanics, did not change Maxwell's equations. In fact, in the confrontation which developed 100 years ago between Newton's particle dynamics and Maxwell's field dynamics, Einstein resolved the contradiction in favor of Maxwell's space-time picture. He took the space-time picture as given by Maxwell's equations to be correct, and accordingly he had to change Newton's equations. That is how the relativistic dynamics came with its important consequence E equal to mc squared, which is the only equation which most people outside physics seem to know. Even quantum mechanics did not change the structure of these equations. However, quantum mechanics led to a profound change in the interpretation of the consequences of this equation. According to the original, so I will compare now what quantum mechanics did to these equations, and it is quantum mechanics which led to quantum field theory. So quantum field theory is the language in which standard model is written. So what I am going to say is the basis of whatever I am going to say later, but of course we cannot spend too much time over it. So let us therefore compare the original Faraday-Maxwell classical picture of the electromagnetic field with the picture provided by quantum mechanics or quantum field theory. In the original Faraday-Maxwell picture, how do we understand the electric force, electromagnetic force between two charged particles? Well, if you have a one charged particle, let us say proton, it is surrounded by an electrostatic field, the Coulomb field. If it is at rest, if it is moving, of course, by Ampere's law, which is Ampere's law, by this law, it produces a magnetic field also. And then you put another charged particle in the neighborhood, let us say another electron in the neighborhood, the electron will feel the presence of the field at that point where the electron is. That is how the electromagnetic interaction is understood in the original Faraday-Maxwell picture of the electromagnetic field. How does quantum field theory change it? It changes it in the following way. A proton is supposed to emit a quantum of the electromagnetic field. I'm sorry, I forgot to mention the most important thing. How did quantum mechanics conceptually change the electromagnetic field? In the original Faraday-Maxwell picture, the field energy, the energy contained in the electromagnetic field could be was a number, which could be any number, a continuous number. The electromagnetic energy contained in the Faraday-Maxwell electromagnetic field is a continuous number. It can take any value. Quantum mechanics changed it in the following way. According to quantum mechanics, the electromagnetic energy can take only discrete values. That is what is called quantization. So electromagnetic field energy now can exist only in discrete packets of energy, which we call the quanta of electromagnetic field, which are the photons. So that is the picture which emerged after Planck and Einstein. So that is the birth of quantum field theory. So now let us compare the interaction between two particles. I already gave the original Faraday-Maxwell explanation of the interaction, but in the new quantum field theoretic picture, the proton, one of the charged particles, emits a quantum of that electromagnetic field, which I have indicated as a wavy line. So the proton emits this photon, or the quantum of the electromagnetic field, which is denoted by a wavy line and denoted by the Greek letter gamma. And another charged particle like electron absorbs that, and it is this emission and absorption of the electromagnetic quantum, or the photon, which is supposed to be responsible for the interaction between electron and proton. So that is the modern quantum field theoretic understanding of the electromagnetic interaction. Here one may note these conceptual changes which occur at every stage in physics. See, when we start with the Newton's equation, we have force on the right hand side of Newton's equation, right? And then at some point in classical mechanics, when we learn more classical mechanics, students are told force has to be replaced by minus derivative of the potential. Potential concept comes. Without potential, you cannot have Lagrangian and Hamiltonian, and even Schrodinger equation cannot be written down. So potential comes. Potential replaces force as the fundamental concept. But here it is not even potential. Potential is supposed to come because of the exchange of the quantum by the so every potential, every interaction is due to the exchange of the quantum of that electromagnetic field. So potential is replaced in some sense by the square root of potential, you can say. It is the emission and absorption of the quantum which is the fundamental interaction. All interactions at the fundamental level are due to the emission or absorption of the quantum. And you multiply the square root of V and square root of V here, and you get the full potential. So that is how quantum field theory has changed the older picture. So such pictures are called Feynman diagrams. Feynman introduced them in as a way of intuitively understanding the complicated calculations in quantum field theory. And in the later pages, I will be using such diagrams to understand the standard model. So I think now we are ready to face the standard model. But I have to say one thing more. Let me go back a few times. Yeah, this one. There is an important connection, important relationship between this range of the force and the mass of the quantum which is exchanged in order to create the force. As I already said, every force, every interaction is due to exchange of quantum. That is the basic principle behind quantum field theory. Now I am saying that the range of the force is inversely proportional to the mass of the quantum which is exchanged in order to create that interaction. Actually, the relation is R equal to H cross over MC. I'm sure all the students know this. So since the electromagnetic force has infinite range, the mass of the quantum, which is the electromagnetic quantum, which is the photon, has to have zero mass. Actually, Yukawa in the early 1930s used this analogy to to predict that the strong interaction, since it has a finite range, the mass of the quantum which is exchanged in creating the strong interaction should be finite. He could calculate it, and that is how we predicted the existence of a pion of mass roughly 100 times the mass of the electron. Later it was discovered, although in between there were a lot of problems, confusion with mu and so on, but finally the particle which is responsible for the pion exchange in producing strong interaction was found, the pion was found. But that is not the complete story of strong interaction. I will come back to this number a little later. Because the strong interaction now is described by a part of the standard model, and there the story is. So what Yukawa said is not the complete story about strong interaction. So we will wait. So weak interaction has a finite range, so it has to be exchanged. The exchange which causes the weak interaction has to be the exchange of a finite mass particle. That also we have to remember. Gravity has infinite range, so if we succeed in quantizing gravity, its quantum is called graviton, and that graviton should have zero mass. So that's all I think I want. Yeah, now we can go further. So now let us go to the standard model. Standard model of high energy physics consists of two parts. One, electroweak dynamics, which gives a unified description of both electromagnetism and weak interactions. The other part is strong interaction, but strong interaction has been given a new name, chromodynamics, quantum chromodynamics. This is based on this Lie group, SU2 cross U1. This is based on this Lie group, SU3, but I will not be using any Lie group in my talk. So let us talk about both these components of the standard model. First, electroweak dynamics. The electroweak dynamics is given here, but before I start talking about it, let us go back to the Faraday-Maxwell electromagnetic field, which consists of two kinds of fields, remember, electric field and magnetic field. Electric field I call E, which is a vector, three-dimensional vector, so it has three components, and magnetic field B, which has again got three components. So there are six components. Maxwell's equation tells you how these six components dance about in space and time. That is the dynamics, Maxwell's dynamics. Now in electroweak dynamics, we repeat Maxwell's fields 4 times. We multiply it by a factor 4. So I have put an index I goes over 1, 2, 3, 4. So 4 kinds of generalized electromagnetic fields, you might say, exist in electroweak dynamics. I equal to 1 can be regarded as the original Faraday-Maxwell electromagnetic field, and its quantum is gamma, the photon. The other 3 fields can be called the weak fields, 2, 3, 4, I equal to 2, 3, 4, and their quanta I have called W plus, W minus, and Z. Plus and minus represent the electrical charge, positively charged, negatively charged. This does not have charge. Z does not have charge, exactly like photon. So there are 4 generalized photons, you might say, in the electroweak dynamics. What is their role? The role of gamma we already know. That is what gives rise to all electromagnetic interactions. What is the role of these? What is the role of these, for instance? Let us go back to the beta decay, the weak interaction, beta decay of nuclei, in particular beta decay of neutron itself. Beta decay of neutron is nothing but neutron going to proton, emitting an electron and an antineutrino. But neutron and proton are already made up of quarks. I already said that. Neutron is made up of 1U and 2D. Proton is made up of 2U and 1D. So in the actual process of beta decay of neutron, what happens is it's a D which decays to U. The other quarks play only a spectator role, and in that process W, this weak quantum is emitted, and that quantum materializes into electron and antineutrino. So this is the modern day understanding of the beta decay of neutron, one of the most fundamental processes in nature. Now the corresponding fields have to satisfy dynamical equations, which are again partial differential equations, which are given here. You can see they are exactly analogous to the Maxwell's equations, except that I have put an I on both sides, and then there are some dots. I will explain the dots a little later. Otherwise they look like Maxwell's equations. It is in that sense that this is generalized electrodynamics. Electroweak dynamics is a generalization of Maxwell's electrodynamics. I have given now some Feynman diagrams to illustrate the role of all these. Now the exchange of photon between the, let us say, the U quark and E will give you the usual electromagnetic interaction. U also is electrically charged. On the other hand, if you now try to exchange the W, since W is electrically charged, if it is emitted, the nature of the particle has to change. D quark becomes U quark, and the neutrino becomes electron. So I say, when we talked about the concept of the potential, we said this is the potential. This also is a potential. This is an interaction. But in this, the particle nature changes. That is what quantum field theory does. Quantum field theory, therefore, is more general than ordinary potential theory. It is capable of including interactions in which particle nature changes. Not only that, I can take this. Oh, I forgot to mention one thing. In all my Feynman diagrams, please remember, time goes from negative direction in the infinite past to positive time direction in the future. So time flows in this vertical direction. So this, all this is initial states. So initially here neutrino was there. You take that neutrino from the initial state and put it as a final state, then it becomes anti-neutrino. That is one of the rules of quantum field theory. So you get this diagram. In this diagram, initially there was only one particle, finally there are three particles. So quantum field theory is capable of taking care of interactions in which particle number changes. Of course, the reverse also can take place. Three particles can become one also. Then I have drawn one more diagram with the exchange of this Z boson. There it is almost like this, because their particle nature does not change, but it has now an interaction even with the neutrino. So this is called the neutral current weak interaction, whose discovery in 1972 was the first evidence that standard model is on the right track. That happened in 1972. Okay, let's now go to quantum chromodynamics. The electroweak dynamics, I introduced the generalized electromagnetic fields of four kinds. In quantum chromodynamics, again I introduce generalization of electromagnetic field, but 8 times, 8 of them, characterized by this Greek index alpha going from 1 to 8. So there are 8 generalized electromagnetic fields whose quanta are called gluons, 8 gluons, called G alpha, alpha going from 1 to 8. Why are they called gluons? Because it is their exchange between two quarks. This Q stands for either a U, the up quark, or U and D are called the up and down quark. That is how the names come. And Q stands for either a U or a D. So between quarks, if you allow the gluons to exchange, just like the photonic exchange, they give you very strong attractive interactions, and they glue the quarks together to form the proton or neutron. Please come here, there are seats here. Where is standing? So they glue together, and that is why they are called gluons. These are the names. These are all names invented by Gell-Mann, which have stuck. Quarks, gluons, the color, chromodynamics, all these names came from Gell-Mann. By the way, Gell-Mann came here to this country in 1961. In fact, he came to Chennai also. He visited medicines in the older form of medicines also. But anyway, so what is the dynamics of this? The dynamics of these fields again are given here, again with an index alpha, and again these 3 dots are there. So again they are very similar to Maxwell's equations. Since I go on stressing that they are very similar to Maxwell's equations, both the electroweak dynamics as well as the chromodynamics, you can naturally ask, oh, why were they not written down soon after Maxwell's equations? If they are so similar, why did it take 100 years? The reason is the following, so I have to explain. They are generalizations, but they are quite non-trivial generalizations. So to go further, let me go back to electrodynamics and say a little bit about electrodynamics. In electrodynamics, there was one kind of electromagnetic field, electric and magnetic field. And there was one kind of charge, electrical charge. The whole of electrodynamics can be summarized from my point of view in one line, one sentence. That sentence is that every electrically charged particle is capable of emitting or absorbing a photon, or at the classical level is capable of interacting with an electromagnetic field. That's all the statement. Every electrically charged particle is capable of emitting or absorbing the electromagnetic quantum, namely the photon. But that raises the question, what is an electrical charge? I'm sure nobody will answer that question because nowadays we don't even discuss. But I have to go further to say, so I will say the electrical charge is nothing but a number. It's a number which we assign to every elementary particle. That number may be positive or zero or negative. It is just a number. Now when we come to this generalization of the electromagnetic field, we have introduced 4 kinds of generalized electromagnetic field to describe the electroweak dynamics, here 8 of them. So we have generalized the Maxwell's equations to include 12 kinds of generalized electromagnetic field. 12 kinds. Correspondingly, there are 12 kinds of generalized charges. Whereas Maxwell's dynamics depended only on one kind of charge, which we call the electrical charge. Here there are 12 kinds of charges. Now, however, there is an important difference between that charge and this charge. I said the electrical charge is just a number. All of you know that numbers have this property, A into B is the same as B into A, if A and B are numbers. Now, these charges, let us call them capital A and capital B. Capital A into capital B is not the same as capital B into capital A. So these are non-commuting charges, and mathematicians call the algebra of non-commuting objects as non-abelian algebras. So this theory is a non-abelian generalization of the original Maxwell's theory. Now, I have not introduced the word gauge field. All of you who have started studying electromagnetism or who have studied it will know that in Maxwell's theory, there is an important thing called gauge transformation and gauge invariance. For the students, I want to mention, many times we ignore it because when we start learning about these things, we don't know how important it is, and anyway the teachers don't have time to explain. We even omit it thinking that it will not come in exam. So we forget about gauge invariance. But it is that gauge invariance which played an important role in getting this standard model. The standard model is a result of realizing the importance of the gauge invariance of electromagnetism. The original electromagnetism is based around the abelian charge, commuting charge, so it is abelian gauge theory. Electromagnetism, Faraday-Maxwell electromagnetism is nothing but an abelian gauge theory, to use the modern parlance, whereas this is non-abelian gauge theory because it's based around the non-abelian charges, 12 of them. The theory of non-abelian so these fields, these generally what I have been calling generalized electromagnetic fields, are also called non-abelian gauge fields. And the theory of non-abelian gauge fields was proposed first by these 2 theoretical physicists, C.N. Yang and R. Mills, in 1954, but still many things had to be done. The theory had to be adapted in order to finally construct the physically correct standard model. So in what respect this theory differs from that? I said that electromagnetism itself can be summarized by the statement that every electrically charged particle is capable of emitting the quantum of the electromagnetic radiation, namely a photon. But photon itself is not electrically charged. So photon cannot emit or absorb itself. In contrast, these non-abelian quanta, for instance these gluons, themselves carry these non-abelian charges. Whereas photon does not carry electrical charge, the non-abelian quanta carry the non-abelian matrix. These charges, as I said, are non-abelian, so they can be called the matrix charges. So these generalized quanta, these 12 quanta, carry these generalized charges, so they can emit or absorb themselves. A gluon, for instance, can emit or absorb itself by this vertex. So far, the only kind of vertices which we had was a straight line, a matter particle emitting a quantum. Only one kind of vertex. However, that is in the electromagnetism. But here, once you go to the non-abelian generalization, those vertices also exist. In addition, we have to add this vertex. Not only that, a 4th order vertex also exists. So that was the contribution of Yang and Mills. They showed that in the non-abelian generalization of Maxwell's theory, we have to add these 2 kinds of interactions. Now this gives me a chance to say a little bit about gravity, especially quantum gravity. So I will preface that with again a question. What is the analog of electrical charge for gravitation? Of course, people will immediately say mass by comparing Newton's law with Coulomb's law. But that is not quite correct. We are talking about the relativistic theory of gravity, namely Einstein's theory, where it is not mass, but it's a dynamical energy. Energy including mass. If the kinetic energy is very small, then it is mass, then you will get Newton's law of attraction. Otherwise, in Einstein's theory, it is the energy which is the analog of electrical charge. So you see that just as I said the gluons, these generalized quanta carried the matrix charges, the quanta of gravitation, namely graviton, carries the charge. The gravitational field is a physical object, so it has energy. So the analog of charge is already there in gravitation. So a graviton can emit itself, just as a gluon can emit itself, a graviton can emit itself. There is a fourth order also. But in contrast to the non-abelian gauge theory of Yang and Mills, which is also called Yang-Mills theory, so the standard model is based on Yang-Mills theory. And the fields are also sometimes called Yang-Mills fields. So in contrast to the non-abelian gauge theory, where Yang and Mills showed that as soon as you add a cubic and quartic interaction, the theory is consistent and complete. You don't have to add anything more. In Einstein's theory, that does not happen. Once you add the fourth order vertex, you have to add the fifth order. Once you add the fifth order, you have to add the sixth order. That also can be simply explained by saying, because every interaction adds to the energy. So once you add this energy, you have to add this energy, and so on. So an infinite series exists. That is what makes Einstein's theory very complicated. And it has so far resisted being brought into the quantum mechanical framework. There are other ways of saying why quantum gravity is a difficult theory. It is still not achievable, but this is one way of saying it. Of course, Einstein did not do it this way. He had this beautiful Riemann curvature, which summarized everything in a beautiful geometrical expression. But if you expand it in terms of this gravitational fluctuation, which leads to graviton, it will look like this. So you can say that in complexity, as far as complexity is concerned, Yang-Mills theory comes in between the simple Maxwell's theory and the very complicated Einstein's theory. Another way of summarizing the situation is to say that in physics we have advanced up to Yang-Mills theory, but the advance to Einstein's theory is yet to take place. Although I said we have come to this level, there is a big loophole, and that is this. I will explain that word now, confinement. This is supposed to be the theory of quarks and gluons, and they are the constituents of the nucleon, they are the constituents of nuclei, they are the constituents of all matter. Okay? But these fundamental constituents of quantum of all these, namely quarks and gluons, have not been seen experimentally. No experimentalist has seen the track of a quark or the track of a gluon. In contrast to electrons, protons, everything has been seen by experimentalists. No detector has seen this. And that is sought to be explained by saying that these fundamental objects of quantum chromodynamics, namely quarks and gluons, are permanently confined within a space of radius about 10 power minus 13 centimeter. So that is the explanation of the 10 power minus 13 centimeter on the top right hand corner of my table for strong interaction. 10 power minus 13 centimeter is the confinement radius, which is a property of these Yang-Mills equations. It is supposed to be a property, but nobody has proved. I hope Ravindran agrees with that. If anybody claims that it has been proved, they can claim $1 million from the Clay Mathematical Institute, which has announced the proof of confinement in Yang-Mills theory as one of the 7 millennium mathematical problems. Nobody has claimed it. Although the best brains, some of the best brains and some of the fastest computers are being used to prove it, lattice gauge theory has made enormous advance, I am sure, but still I don't think there is a proof. If there is a proof, I would like to see that, so that I can teach it to MSc students. A bright class of MSc students, you will not be able to prove quark confinement or confinement. That is why I still consider it as a hypothesis only, but that is a challenge to all the young people here to prove it. I think that's all I want to say about this transparency. Okay, so this is a part of the standard model. The universe, according to the, I hope I don't exceed my time limit. I had said I will go up to 5 o'clock, but I don't think I need up to 5 o'clock. I will try to finish much earlier than that. The universe, according to the standard model, consists of two parts. The physical stuff of the universe consists of two parts, which I have called here the field sector and the particle sector. The field sector I have already talked about. The field sector, or the electromagnetic field whose quantum is photon, and the weak field whose quanta are the three quanta W plus W minus Z, and the strong fields, chromodynamic fields, 8 of them, the gluonic fields, so 12 of them. Now they are all bosons in the sense they all have internal spin 1 in units of Planck's constant, and according to quantum field theory they have to satisfy these statistics, Bose-Einstein statistics. They have been called bosons after Bose identified the first boson as the photon. All these are photons, they have spin 1. Not only that, they are all analogous to photon, and as I already said in the very beginning, photon has 0 mass, so they should all have 0 mass. But that will be a catastrophe, because the exchange of W plus W minus and Z, which leads to weak interactions, then the weak interactions will have infinite range. So that is an important problem which standard model had to face, and it was Peter Higgs who in 1964 showed the way how by now the famous Higgs mechanism, the W plus W minus and Z get mass, whereas photon remains massless. That is called the Higgs mechanism, and an important consequence of that Higgs mechanism is another particle has to be found, and that is what I have put within circle, the Higgs boson, which was discovered in 2012. But I have to say a little bit more here, but I don't have too much time, unfortunately. All these things have been described in an earlier colloquium here, and many other people have talked about it here. So the mass of the W plus and W minus is predicted by the Higgs mechanism, and the mass of these come out to be about 78 or 80 GeV, let us say. 80 times the mass of the nucleon, this about 91 times the mass of the nucleon, and these were all discovered experimentally at CERN in 1981-82. So those were the second important verification of the standard model. And once you know the masses, by the formula which I mentioned, R equal to H cross over MC, you know the range of the weak interaction. It will come to be some number times 10 power minus 16 or 10 power minus 15 centimeter. You can calculate it. But an important consequence of that is that another particle, a finite mass particle, but with 0 spin has to exist. That is what is called the Higgs boson, and that was searched in all high energy machines from the time the standard model was constructed, but it was not found. Finally, 2012, it was found, and that was big news. All of you know that. So these are all bosons. So there are 13 of them, 12 generalized photons, you might say. Only one of them has 0 mass, but all of them are spin-1 particles, but all of them don't have 0 mass. This also is 0 mass. However, the range of the strong interaction is not determined by its exchange, but by the confinement radius, 10 power minus 13 centimeter. Below this line, I have put the gravitational field, the metric field G mu nu, but that quantization is for the future, so let us not talk about that. Let us come to the particle sector. Particle sector, we have the proton and neutron constituents of the nuclei, which I already said are made up of the up quark and d quark, 3 of them. And so let us not talk about these composites, let us talk about only the elementary particles, U and D, put them as column vector. U and D make up all the nuclei of the world, of all the atoms and every piece of matter. Once you add electrons, you can make all the atoms and all the molecules, all the solids, liquids, gases, everything. Inanimate as well as animate matter, all of it in the universe are just combinations of different numbers of them in different configurations. Well, just these 3 particles. So at the basic level, things look very, very, very simple. Of course, you have to create the whole universe out of that. Now, if you add the neutrino also, weak interactions are included, thermonuclear fusion reactions can take place in the sun, and life is possible. So you can create a pretty good universe just with this quartet of particles. This is called the quark doublet, and this is called the leptonic doublet. However, nature for some very important reason has decided to repeat it at least twice more. This is called the first generation, this is called the second generation. This mu heavy electron has been, it was first actually seen in the cosmic rays, observed in a phenomenological analysis by Homi Bhabha himself in the early 30s, but then Anderson discovered saw its track in cloud chamber in Caltech. So that is the muon, and then later in high energy machines, tauon has been seen. So these muon and tauon are nothing but heavy electrons with higher masses. This is 200 times as heavy as electron, and this is 3500 times as heavy as electron. Each of them come with its own neutral partner, which are called the neutrino. So 3 charged leptons along with the 3 neutral leptons. So this is called the second generation, this is called third generation. These are heavier quarks. Many people here are experts in all these heavy quark physics. All of them have been experimentally seen and studied now. All of them exist. Now one other point I want to make, from a fundamental point of view, all these are equally important. Not only these, of which all of us are made, but all these. In the sense, in the beginning, the Big Bang is supposed to have made all of them in equal number. But all of them decayed away because these are all heavier than this. By weak interaction, as I already said, all of them decay because they are heavier in mass. Anything which is capable of decaying will decay, as long as the conservation laws are okay, especially the energy conservation. That means mass has to be higher. Since the masses are heavier, they all decay. That's all. Well, Buddha had said that everything decays, and in high energy physics it happens. Everything decays, leaving finally the universe to be built out of the lightest particles only. That is why the universe seems to be made up of only these. But from a fundamental point of view, all are equally important. Not only these, they are anti-particles also. I have to open out another column here for all of them. So in the beginning, the universe, when it started as a big bang, the fireball, all these and their antiparticles were made in equal number. But now we know that the universe is made up of only these particles. What happened to all the antiparticles? That is one of the big cosmological mysteries, which is answer to that is related to this number 3. So I will leave it at that. That is called the matter-antimatter asymmetry. The laws do have a matter-antimatter asymmetry built into them, which is called the CP asymmetry or CP violation. Many experts in this institute exist for that, and that CP violation is supposed to be responsible for creating a matter-antimatter asymmetric universe for evolving from a matter-antimatter symmetric universe to a matter-antimatter asymmetric universe, which we see now. So that's all I want to say. Now there are 2 points I have to make here. I called this the particle sector. Yeah, these particles, just as these are bosons, these are all fermions. Any particle which is half integral spin in units of h cross again is called fermion. They satisfy these statistics. All of them happen to be just spin half particles. You don't need these higher spins at all. So they are all fermions. But I want to mention one thing about this word particle. I call these as particles, and here I call them fields, but that is not quite correct, because these are also particles. Quanta are also particles. And these particles also are quanta of the corresponding quantum field. Electron is the quantum of the electron field. Quarks are quanta of the quark fields. So in quantum field theory, there is a unification of the field and particle concept. Both are different facets of the same physical entity. So these names are not quite appropriate. I should really call it bosonic sector and fermionic sector. That's only a name anyway. I think that's all I wanted to say here at this point. Yeah. I think I have almost finished the standard model. I can go to the next topic now. I'm just wondering whether I forgot to mention anything here. Okay. This is the real standard model. I just wanted to show this. Don't think that I have really told you what the standard model is. This is the real standard model. The standard model is, of course, described by a quantum field theoretic Lagrangian. So if I am able to explain all this and you are able to explain all that, then you can say that you have understood standard model. So for those of you who are not particle physicists, I am not trying to scare people away, but that is a fact. That is the truth. So truth has to be told. So it is a challenge to really understand quantum field theory to the level where you can really understand the basic Lagrangian which is written here. Another reason why I want to show this is, remember, this is the basis of all of physics except gravity. That's what I mentioned in the very beginning. I never thought that it would be possible to do this. When I started my research more than 50 years ago, we were all in high energy physics. Well, at that time it was called particle physics, elementary particle physics. I never thought that we will come to one day where we can do this. We were all groping in the dark. We did not know what strong interaction was, for instance. We had all kinds of funny ideas. Weak interaction we knew a little bit, because Fermi fortunately had given us the theory which really served very well, and that has been incorporated in the standard model. But we were all groping in the dark. I never thought that it will be possible to put all of standard model into one page, all of high energy physics into one page, and that is possible. And that is the progress of the last 50 or 60 years. Yeah, this part of that, explaining that. Okay. Standard model, the standard model which I have tried to describe here was constructed by theorists more than 40 years ago. Experimenters verified each component of this theory in the next 40 years, except for one component, the Higgs boson, which I mentioned. This last missing piece was discovered only in 2012, and that was big news. You know, it is like saying constructing a big machine, a gigantic machine, in which one important bolt was missing. So that missing bolt was found in 2012, and that was the Higgs boson. So standard model emerged as the standard theory describing nature. Where do we go from here? Remember, the standard model is a theory of only 3 fundamental interactions. The fourth one, gravitational force, is missing in standard model. It's a deep irony of nature that the twin revolutions of quantum and relativity that powered the conceptual advances of the 20th century and that underlie all the subsequent scientific developments have a basic incompatibility between them. The marriage between quantum mechanics and relativity has not been possible. By relativity here I mean only general relativity, since special relativity has already been combined with quantum mechanics, leading to quantum field theory, which has been used in constructing standard model. Gravity, which gets subsumed into the very fabric of space and time. Remember, in Einstein's theory of gravity, general relativity, gravity is nothing but the curvature of space-time. In this theory has resisted all attempts at being combined with the quantum world. Hence, quantum gravity has become the most fundamental problem of physics. The most successful attempt to construct quantum gravity is string theory, although there are many other attempts also. Actually, string theory offers much more than a quantum theory of gravity. It provides a quantum theory of all the other forces too. In other words, it can incorporate the standard model of high energy physics also within a unifying framework that includes gravity. So here I have a one-page description of my understanding of string theory. In string theory, a point particle, again string theory, there are many experts here who can give better seminars on that. In string theory, I need some more water, so you can read it yourself. In string theory, a point particle is replaced by a one-dimensional object called string as the fundamental entity. Its length is about 10 power minus 33 centimeter. This is the other length which you have to remember, which is the length scale of any theory of quantum gravity, including string theory. It is also called the Planck length. The various vibrational modes of the string correspond to the elementary particles. String theory automatically contains quantum gravity, and that is its special beauty. Just see, in quantum field theory we could not incorporate gravity, but here in string theory you cannot construct a theory without gravity. That itself tells you something about string theory. However, this is bought at a price. It works only if the number of space dimensions is 9 and including time it is 10. Where are the extra 6 dimensions? They are supposed to be curled up to form space bubbles at distant scales of the same 10 power minus 33 centimeter. Both the string and the extra curled up dimensions will be revealed to us only when we can access such length scales. So that is in brief a summary of string theory. So has string theory solved the problem of quantum gravity? Yes, perhaps, but how do we know? Where is the experimental support for string theory? Remember, it took 40 years to verify the standard model as the correct theory of nature. That required the construction of particle accelerators and particle colliders of higher and higher energy, ultimately culminating in the construction of the Large Hadron Collider LHC at CERN, Geneva, reaching energies in the TeV region, which is still working, which is temporarily it has been shut off for upgrade, but I think in a few more months it will begin to operate again. This machine is a behemoth. It is a huge dinosaur. It has a circumference of 28 kilometers and its construction took 20,000 physicists and engineers from 100 countries, including our own, working for 20 years. In relativistic quantum mechanics, this is another relationship of the kind which I mentioned earlier. In relativistic quantum mechanics or quantum field theory, there is an inverse relationship between the length scale and the energy required to probe it. If you want to probe a distance scale of L centimeters, you need an energy scale. E, again you have to put H cross. I think H cross will come in the denominator, right? Yeah. H cross and C have to be put in order to give it as an equation. But the point is, E is inversely proportional to the length scale which you want to probe. The energy which is required in your beam in order to probe a length scale L goes like this. Remember, I said at the very beginning of my talk that we have descended down to a length scale of 10 power minus 17 centimeter. To probe that distance scale, we needed the TeV energies, 10 power 12 energies, tera electron volt. LH is now, I think it will go up to 14 TeV or even more perhaps. So to probe the length scale of quantum gravity, which is 10 power minus 33 centimeter, which is 16 orders of magnitude smaller, we need 16 orders more energy, 10 power 16 TeV. This is the energy required to experimentally test string theory or any theory of quantum gravity for that matter. Most people think this is not possible. That is the crisis in fundamental physics. I don't agree with this, but most people think this way, so I call it a crisis. Galileo had decreed laws of physics are written in the language of mathematics, but those laws can be proved or disproved only by experiments. For 400 years, physics has progressed only by following the path decreed by Galileo. If we give up this path now, that will be the end of fundamental physics. That is why I call it a crisis. In that case, all the beautiful theories that we build for quantum gravity will remain as mere metaphysics. What is the way out? Cosmology. If current ideas in cosmology and astrophysics are correct, then early universe provides us with a high energy physics laboratory where particle energies were almost unlimited. So it is believed by many among us. I don't know whether Raghu is here. Cosmologist, he was here. Anyway, he has gone. Provide us with a high energy physics laboratory where particle energies were almost unlimited. So it is believed by many among us that all our theories of high energy physics can be tested by appealing to events in the early universe. At the risk of getting a flack from many of my respected colleagues, I would like to strike a note of caution. There is no doubt that the era of precision cosmology has dawned with the measurement of cosmic microwave background radiation anisotropies, whose accuracy is awe-inspiring. First Kobe, then WMAP, and now Planck are creating waves. We seem to have come a long way from Landau's dictum, astrophysicists are often wrong but seldom in doubt. That's what Landau said. However, we know only one universe, and the events presumably occurred only once. That too quite a long time ago. Modern science owes its existence to the advent of repeatable experiments under controllable conditions. Ever since Galileo, that's what we have done. Whereas history provides only a single sequence of events. History cannot be a substitute for science. Cosmology cannot provide crucial and definitive tests for fundamental theories of physics. This is my view. On the other hand, laws of physics inferred from and tested in laboratory experiments can and must be applied to the study of the universe and its history. The history which they are creating is really fantastic. It's very interesting. We should do that. However, that cannot replace laboratory experiments. In other words, the only healthy traffic between high energy physics and cosmology is a one-way traffic. From high energy physics, build the history of the universe, cosmology. So where are we? So we have to make a direct attack on the high energy frontier. Instead of merely scaling up the sizes of the accelerating machines, which is almost impossible now, we must discover new principles of particle acceleration. That 28-kilometer machine is able to give you tens of TeV. Now they are thinking of 100-kilometer machine. They are already plans are there. Whether it will come up, I do not know. They might be able to go up to, let us say, 100 TeV, or let us say even 1000 TeV. Beyond that, what do you do? So obviously that is not the route which physicists have to follow. Either new principles of acceleration have to be discovered, or there will be an end to high energy physics by about 2040. You can easily see that this conclusion has nothing to do with quantum gravity or Planck energy. I am using that only as an important milestone. But even without quantum gravity, high energy physics will stop by the year 2040 if we do not invent new principles of acceleration. So that is my main message here. So let us, I have 2 or 3 pages on this. Growth of accelerator energies. Growth of accelerator energies over the past 80 years has been phenomenal. The energy has been increasing by a factor 10 every 6 years. I interpret this exponential growth as an optimistic sign for the future of high energy physics, fundamental physics. So if the same growth can be maintained, 16 powers of 10 can be reached in 96 years. I had made this prediction in the year 1986. It has not borne out because SSC was stopped and so on. But this thing, what I am saying, is possible only if new principles of acceleration and newer technologies are continuously invented. This exponential growth, this exponential growth is possible only for the envelope of all different kinds of accelerators, starting with Cockcroft and Walton. If you go on plotting the energies of various kinds of accelerators in the last 80 or 90 years, that is called the Livingston plot, you find this result. It's a logarithmic plot, logarithm of energy on the y-axis and the linear energy scale, the time scale on the x-axis. Then you get a straight line, and from that I have taken this. But that is possible only for the envelope of different kinds of technologies. If you start with Cockcroft and Walton original electrostatic generator, which I don't know, accelerated maybe up to NeMeV or even part of it, then various kinds of accelerators have come. I don't even remember now. Finally, the cyclotron principle was discovered by who discovered Lorentz. And many principles were discovered. And at any point in that, this is called the Livingston plot, at any point you find that if you now get stuck with one kind of accelerators, the energy always saturates, just saturates. Then go to the next level, then the other accelerator goes for some time and then saturates. But it's the envelope which has this property which I have mentioned. So that's why I said you have to continually invent new methods of acceleration. What are the new principles of acceleration? I will give one example. In the last 30 years, many ideas on laser plasma acceleration are being pursued. Using laser excitation of plasma wake fields, electrons have been successfully accelerated to 1 GeV in 1 centimeter. Just imagine 1 GeV in 1 centimeter compared to kilometer size conventional accelerators to get similar GeV energies. So tabletop accelerators are perhaps not far away. Maybe this will lead to breakthroughs that will help us to cross the super high energy barrier. Here again, I am not claiming that this alone will reach you to Planck energies. I am not saying that. But this will be an important stepping stone in this journey. What we need are 100 crazy ideas. Maybe one of them will work. Maybe the breakthrough will come from one of you, especially the students. This is an excellent opportunity and challenge for experimentally and technologically oriented students. That is where the bright students have to put their mind to. So that is my main message which I want to say. In order to ensure the future healthy growth of high energy physics or fundamental physics, we need people with bright minds who will really solve this problem and help us to cross this crisis point. Actually, many of these things I have taken from my article, which is there in the proceedings of the DAE High Energy Physics Symposium 1986 in Saha Institute. I said exactly the same thing, and I have been saying this in many meetings. Nobody listened, but fortunately now I have found a group of people from various institutions, TFR, BRC, IPR, RRCAT, people who are in charge of various laser and plasma facilities, who are prepared to do this. I wish they had listened to me 30 years ago, because 30 years ago the field was very young. If we had started 30 years ago, we would be on the top. But many places now, Berkeley, Stanford, Oxford, Japan, many places in Japan, even in Korea, and many places in Europe, these facilities are come up in a big way. I just happened to go to a meeting in ultra intense lasers in Goa 1 month ago. It was truly impressive. I wish we had participated in it so far. Some facilities are there in India, but we have to put all these together in order to have laser plasma acceleration. Okay, there are many things which I have left out, so maybe I will spend about 5 or 10 more minutes just saying a little bit more. My main argument is over. I will just say a little bit more. Allow me some 5 or 10 minutes more. Just fill in some of the gaps which I have. I introduced the 10-dimensional world of strings, but I did not say much, so I should say a little bit at least. I am not a string theory expert, although I have been a great admirer from the time it started in 1984. Strings live in a 10-dimensional world, as I already said, having 6 compact space dimensions in addition to our familiar 4-dimensional space-time. What is the shape of the 6-dimensional compact manifold? At least some time ago, string theories found this the most likely possibility, the so-called Calabi-Yau manifold, which had been then discovered by 2 mathematicians. It may be that if you know the correct 6-dimensional potato with all its warts and holes, string theory will determine the properties of all the dozens of elementary particles, and even the full standard model may follow. We now know that. Now this is the next point. So this is about Calabi-Yau manifold. Next point is, we now know that in addition to the 1-dimensional strings, string theory automatically contains 2-dimensional membranes, and in fact branes of higher dimensions too, up to 9 dimensions, right? So string theory is not just 1-dimensional objects alone anymore. String theory is the relativistic quantum dynamics of a mind-boggling variety of interacting extended objects, chairs, tables, cars, airplanes, and everything, all living in 10-dimensional world. It is rich mathematics and physics. Its richness is continuously being discovered, as you can see from HEPTH archive, or go to the String Theory Journal Club. You will see the kind of worlds which they are building. Because of all these, because this is a very complicated world which they are constructing. Not only that, I wanted to make one more point. String theory is a natural generalization of local relativistic quantum field theory, which is based on point particles and interaction occurring at one point. From the time quantum field theory was constructed, many people have tried to make it non-local. Even the great people like Yukawa, Mueller, and then Heitler. Even Dirac tried to construct a non-local theory for electron, a finite size electron. All of them failed because they all introduced a finite rigid length, which is inconsistent with the relativity. That is where they all reached their dome. And string theory people solved that problem by not having a rigid length. The strings simply wave like anything. Their tails are waving. I mean, it's not a fixed length. So relativity is consistent, except that you have to go to 10-dimensional relativity, not just 4-dimensional relativity. So in that sense, string theory is a natural non-local generalization of the local relativistic quantum field theory. But because of all these, it is a very difficult theory. But finally it will be mastered. It will be mastered only through mathematics for the moment. String theory requires the creation of new mathematics. Maybe all of great mathematics will have to be used in gaining control of string theory. That is why many times people shy away from it, because it looks so mathematical. By necessity it has to be so, because it's a very, very complicated theory. From the physics point of view, it's a very, very complicated thing which you are doing. So no wonder mathematics is very complicated. String theory is the top candidate for the correct theory of quantum gravity, which is the next frontier in fundamental physics. After the spectacular success of the standard model of high energy physics, however, string theory is so complex that it requires all the mathematics that is yet to be created. So this is the ideal for ambitious students who are mathematically oriented. I am sure there are many of them right here. So that's all I want to say about string theory, but there is one other big gap here in my whatever I have said, so let me try to fill that up. Symmetry breaking in Higgs is a very important topic, but we have covered it many times earlier, and so I am not going to spend more time over it. Rather, I want to see, I talked about standard model and then I shifted to quantum gravity and string theory, but there are many other things which have to be said. Oh yeah, that is the thing which I forgot to mention. So let me go back a little bit. I was wondering what I forgot. I don't know, it doesn't work. Why doesn't it go? No. Yeah. I don't know, somehow it refuses to go back. Keyboard, huh? Yeah. Just go back to the standard model itself. I should have made the point right there, I forgot. And then I will have to go forward also then. I said that it is Higgs mechanism which gives masses to these particles, keeping the photon massless. But it is the same Higgs mechanism which gives masses to all these particles. It is the Higgs mechanism which gives masses. There is a universal Higgs field which exists everywhere, which is existing right here. That is what gives masses to these three particles, as well as masses to all the quarks, as well as masses to all the charged particles, charged leptons. Electron gets mass only from the Higgs field. Quarks get mass only from the Higgs field. However, that Higgs mechanism does not give masses to the neutrinos. Nu e, nu mu, nu tau. Neutrinos remain massless even after the Higgs mechanism. However, 15 years ago, 1998 in particular, experimentalists discovered that the neutrinos do have mass, although it's a very tiny mass. So that's what I want to talk about now. That is the importance of the neutrinos out of all the other particles. As I said, I talked about standard model, immediately I jumped to quantum gravity. There are many other things which might happen in our journey until we reach the quantum gravity. So that is what is usually called beyond standard model. So let me just say a few words about it. The first thing which I already mentioned is about neutrinos. Neutrinos are massless in the standard model. Even Higgs mechanism does not give mass to neutrinos. About 15 years ago, experimenters discovered the neutrinos do have tiny masses, and this has been hailed as a great discovery, since this may show us how to go beyond standard model. Neutrinos may be the portal or the window to get a peep beyond the standard model, and that is the importance of the INO, the India-based Neutrino Observatory, which is about to come up, and our institute is playing a very important role in that, in the creation of the INO. Next, dark matter. Astronomers have discovered that most of the matter in the universe is not the kind we know. It's not the kind which I have talked about so far. It is called dark matter since it does not emit, absorb or scatter light. Although this discovery has been already made by astronomers, nobody knows what this dark matter is, and only physicists can discover it. And many experiments, dozens of experiments all over are trying to directly get the dark matter in their experiment. So far nobody has succeeded. although there are many claims and counterclaims. A dark matter experiment also will be mounted in the INO cavern, suitably extended. Any weird object like neutrino, dark matter, all these things can be investigated in the underground laboratory, a huge underground laboratory which is coming up in Theni district near Madurai. What about the other things? In the last 4 decades after the standard model was constructed in the early 70s, theoreticians have not been idle but have constructed many theories that go beyond the standard model. Of this, grand unification I have already mentioned. Another is supersymmetry. It postulates the existence of a boson corresponding to every known fermion and vice versa. So, since electron is a fermion, there has to be a bosonic electron. Since photon is a boson, there has to be a fermionic photon, which is called photino. These things have to exist if supersymmetry is right. This is a very elegant symmetry. This supersymmetry is a very elegant symmetry that leads to a better quantum field theory than the one on which standard model has been built. Although standard model has been successfully built on quantum field theory has a serious disease, the disease of divergence. In spite of that, standard model works because the standard model is a completely renormalizable theory, but the divergences remain. And many of the divergences go away if we supersymmetrize the standard model. That is the reason why theories like a supersymmetric standard model. But if it is right, if supersymmetry is right, we have to discover a whole new world of particles. As I said, for electron we have to discover another, for photon we have to discover. We have to discover a whole new world of particles equaling our known world. But remember, we took 100 years to discover the known particles starting with the electron. So what I am trying to say is, we require patience to discover this. There are many more theoretical speculations apart from grand unification and supersymmetry. I don't have time to talk about it. There are many people here. Srihari is there and many others. But and Rahul, I don't know where is Rahul. But none of them has seen an iota of experimental support so far, even in the Large Hadron Collider. That is the pity of all these theories. Nothing has been seen so far beyond the standard model, except one thing, that is the neutrino mass. However, Large Hadron Collider will have many more years of operation. Let us hope that new things will be discovered. I think that's all I have to say. Yeah, then finally the biggest loophole, of course, is quantum gravity, and I have already talked about it. I think that's all I have to say. Yeah, this is, many people have contributed to the construction of standard model, and many theorists who proposed the ideas, and many experimentalists who helped to verify them. Many of them have been given Nobel Prize also. I have given the list. And actually one can learn quite a lot about the standard model just asking the question, why did they get the Nobel Prize? What are these things? What do these things mean? But anyway, that is one way of learning high energy physics. That's all I have to say. Yeah, this I have already said. These are. Thank you very much for your patience.
Comments on 10 dimensions is a bit overemphasized. It doesn't have to be that way, but it is standard thing to do. I mean, people say that it has to start with 10 dimensions. Those are called geometric compactifications. There can be non-geometric compactifications also. Usually, in order to get supersymmetry, the standard method is to start from 10-dimensional supersymmetric theories and then compactify. But in principle, it doesn't have to be that way. It's not true, the statement that you made, that is not that.
So there are other possibilities. Very good. Good to know. The other thing I wanted to mention was, as far as I know, supersymmetry is absolutely necessary for string theory to make sense.
No, the
otherwise there will be the tachyonic instability, right?
Yeah, that doesn't mean that there cannot be a string theory without tachyonic instability, which is non-supersymmetry.
It's possible. Oh, that's good news. If supersymmetry is not found, that possibility has to be invoked. But I think the standard way of doing string theory requires supersymmetry. That is another reason why supersymmetry most probably is there. Only thing is we may not find it in LHC. Yeah.
Any other question? Is there a single super strings theory?
And when he says superstrings, I mean, is there anything called superstrings? There are many versions.
Yeah, there are various limits of the theory, and where you have quadratic descriptions.
Any other?
Now, what exactly is the question and what is the answer? I didn't catch it.
Whether there is anything called something called superstrings as it is actually like standard model. There are many versions.
No, if it is so, then we would be talking only about that, right? Most of the time we talk about standard
It's
model.
supposed to be thought as a backbone in exposing theory. These two things are. It's like
I mean, you are asking whether there is a single superstring theory.
Yeah, because now there are many versions that people talk about.
it's not
But there I have my view is the following. If you look at the Yang-Mills theories, there are infinite number. All of them are correct, mathematically speaking. But nature decided that only one version, namely SU3 cross SU2 cross U1 is the correct group. There are infinite number of Lie groups which Cartan had classified. Okay, all of them are possible. So how did we know that one of them is correct? Only by experiment. That is why I feel it's the experiment which will decide. Even if string theory is correct, there may be infinite number of string theories. Only one of them may be right. How will you know which is right? Of course, many string theorists think that their brain is strong enough to choose one, but I don't agree.
Problem really is the multiverse problem, where there may be one theory here, another theory in another universe. In that case, we have gained nothing.
Oh, that may be one way, but I don't want to talk about that. Let us talk about our universe. Let us restrict ourselves to understand our universe is hard enough.
Any questions about this talk?
So I just wanted to make this comment actually, Rajari. I think
Yeah.
this is a very important point, that the direction will be determined by experimental results. This we should not lose sight of.
Yes, that is the main content, main punchline of my talk. But in order to do experiments, we have to have experimental facility. We have to create that. We don't have. Beyond 100 TeV, beyond 1000 TeV, there is no experimental facility right now.
Talking about something as mundane as neutrino masses, for example.
Oh yeah.
Even for that, you have your models, but which model? Again, you have.
No, that is a different talk on neutrinos. Okay? So let us restrict ourselves to the other things. Any other?
You weren't optimistic about cosmology feeding into.
Could
you please elaborate on it? I mean, why is it not?
Because it is history. The whole scenario lasting 13.7 billion years have to be constructed in order to learn from cosmology physics at the fundamental level. It may be possible.
I
Again,
understand quite a bit of that history, almost all of it actually.
you think so? I don't know.
Not me.
Maybe if we're lucky enough to see a black hole after.
Okay, cool. No, what I'm
That's a
saying
lucky
is,
cause.
I mean, I read the book by Weinberg, and he's quite nice.
No, most people think, that is why I am saying this is my view. My view is it works only in one way. You use knowledge about fundamental physics in order to construct history of the universe. From the history of the universe, in order to jump to conclusions about fundamental physics, in my opinion, it will be very hard. That is my view. That's why I said it's one-way traffic. One-way traffic is very interesting. I'm not saying one should not do it. But I want to learn about fundamental physics. This may give some ideas, but the crucial evidence whether what you are saying is correct or wrong will not come.
No, but on the other hand, the strongest constraint on the sum of the neutrino masses currently comes from cosmology.
That's why I don't believe that constraint. I never believe it. I would believe the tritium beta decay any day better than those constraints, which is done in the laboratory.
The biggest point is that after one observation, one data point on one experiment.
Exactly. It's not repeatable. It's not done under controlled conditions.
No, I mean, you can't get definitive answers from
Experiment is
cosmology.
done only once. That's
But
one
they can
experiment,
definitely
one-
guide you towards the correct
Yeah.
experiments, etc. So forth, right?
You may be misguided also.
So I don't know, I think one way,
You may be misguided also.
saying it's a one-way traffic, is that a bit strong?
It's a strong, I purposely make that strong statement because right now everybody's attention is on cosmology. I'm saying do it, it's very interesting, but we have to do experiments. I want to bring them back to,
For experiments is what you're saying.
yeah, it's not a substitute for experiments.
Let's postpone all the